Okay. So well, if you read the abstract, I apologize because the talk will be less colorful, but also with more colors than the abstract. So there's, as you see, there are colors instead of gray. So okay, let me tell you first of all what the basic, the very basic idea of what's happening here is. Just think about you have some configuration of heat in space. Okay, so here's the configuration of heat. Maybe somebody heated up these points a lot, and then you allow you allow the heat to diffuse for a few seconds. Okay, and then the question that we'll come to in a minute is if you do that, is it possible? So if you notice here, maybe, I don't know, maybe this is like 100 degrees. You can, there is a lot of heat concentrated at 100 degrees. If I cut through 100 degrees, or between 100 and 101, I see a lot of heat. And the question is, if I let this evolve for a few seconds, can it still be that there is a lot of heat at some very high level? Okay, I mean, certainly there can be a lot of heat at some temperature, because if I let it evolve, maybe all the heat, maybe it was close to uniform and then it becomes uniform. So then all the heat will be at some low temperature. But is it possible for the heat to be concentrated at some high temperature? Is it possible you do some heat flow and then, still what you get looks like a step function? This seems improbable, but that's what we'll discuss. Okay. All right, so let's start with the discrete cube. So you take a function from the discrete cube to the reals. And then we'll define this noise operator. So this is the Bonami-Beckner operator. Here I'm calling it the heat flow operator. So it's defined like this. Given such a function, the operator gives you a new function. This worked a moment. It doesn't matter. T epsilon f. So to evaluate this new function at x, you evaluate it at the, you take the average value of f evaluated at some points. And how do you get these points? Well, you take x, and every coordinate with probability 1 minus epsilon, you leave it alone. And with probability epsilon, you flip it to a uniformly random plus minus 1 value. Okay? So every bit you apply some epsilon noise to, and then you average over this noise. This is the operator T epsilon. And a general principle that goes back a very, very long time, at least, I don't know, 50 years, is that if f was smooth, then T epsilon f is even smoother. So if you have some function which is not too crazy, and you apply a little bit of this heat flow to it, then it regularizes the function. The function gets even nicer. Okay? And this has lots of applications, in particular in discrete math and in theoretical computer science. Okay? So there's a list, and probably most of you here know this. Okay, so let's just formalize what this general principle is. I mean, the most famous instantiation of it is the hypercontractive inequality, which says that, okay, now we think about this, remember this T epsilon operates on functions, and the hypercontractive inequality says that this is a contraction from LP to LQ for some q bigger than p. Okay, so what it means is that if you start with some function and you know that the p norm of f is small for some p bigger than 1, then when you apply the smoothness, actually you know that, wow, someone is adjusting the volume in real time. Then when you apply some noise, then you know that the q norm of the noise version is small. Okay, and the point here is that the way things are set up, these are, I didn't write it here, but these are these norms are sort of fp is the expected value over the uniform distribution of f to the p to the 1 over p. The higher the value of the p in the norm, the more this thing punishes, right, sort of the function for being spiky, right? So this says that if I have some regularity class for f and then I apply noise, the regularity gets even better. And if you just think about it combinatorially, so f is the indicator function of a set in the discrete cube, then this encodes some kind of small set expansion in the space. Because what it means that the p norm is small is if f is an indicator, or f is, think about it as close to an indicator, is that the support of f is not too small. Okay? And then what it means that the q norm of the smooth function is small is that for q bigger than p, the support of T epsilon f is even bigger. So if we know that the support of f is at least a certain size, then the support of the smooth version is even larger. Okay? This picture is misleading because these norms don't care about where these points are. So you could distribute the mass around the picture, and it would still be the same thing. Okay. Yeah. Okay. Yeah. Yeah. Okay. So this is one way to encode this fact that T epsilon makes functions more regular. Here is another way to look at this. So let's, it's a notion that we'll see again soon. So now let's take a function which is non-negative and has expectation 1 with respect to the uniform measure. Okay? the uniform measure on the discrete cube. And then we'll define the sort of, this is the relative entropy of F with respect to the uniform measure. The way to think about this quantity is that it's maximal when F is concentrated at a single point. When F is a delta function, this thing has value n. And when F is the constant 1 function, this thing has value 0. So this is the entropy deficit of F, sort of n minus the Shannon entropy of F. And then if we define the gradient of F in the following way, so this just measures how F changes along edges of the discrete cube, then you have this logarithmic Sobolev inequality. Okay? So the point is here, notice that the entropy, just like the p norm and the q norm from before, has nothing to do with the geometry of the discrete cube. It only looks at this as a set of size 2 to the n, right? On the other hand, the gradient, of course, looks definitely at how F is changing with respect to the geometry of the cube. And what this says is that, okay, in words, if the function F cannot be, the function F cannot be very spiky unless it changes a lot over edges, at least on average. Right? And a better, okay, this square root F is weird, although it's really there. A better way to think about the right-hand side here is that this is actually the Fisher information of F. So it represents, if we apply a tiny bit of noise and take the derivative and then look at epsilon equals 0, so we do some infinitesimal heat flow, then this is the derivative of the entropy with respect to the heat flow. So this quantity tells you how fast F is spreading out, and this Log-Sobolev inequality tells you that always you have a lower bound on this quantity, so always the entropy is the relative entropy is decreasing. Okay, and it says even more. It says that the larger the relative entropy of F, the faster it's decreasing. So sort of the spikier, if F is more concentrated, then actually the relative entropy is decreasing even faster. And okay, and these two things are well known to be equivalent. Okay, in a precise quantitative sense, these are saying the same thing. Okay, but well, maybe if you just okay. So if you look at the hypercontractive inequality, what you see is that, as we said before, if the p norm of F is small, then also the q norm of the smooth version is small. Okay, and so Talagrand said,
So it's only
yeah.
for hypercube?
So far everything is for the hypercube. Yeah, we're just in the
There's a Log-Sobolev inequality generally, and that's not
generally in what I mean.
graphs.
In every graph you can define it, but it's just like the spectral gap. It could be horrible for some graphs. Right. Yeah. So but no, I mean So if you put a constant here and then take the supremum of that constant over all the functions, then you'll get the Log-Sobolev inequality of whatever graph you care about. But it could be quite, it could be bad. This one is saying that the cube is actually doing a pretty good job at, the heat flow is doing a good job at spreading out the mass.
Yeah, no, my question was the relationship was only
Yeah, this is. I mean, this relationship only holds for the hypercube. I mean, otherwise you would need to put some other constant there. These things are equivalent. Okay, so yeah, so Talagrand asks, what about what if we don't start with any information about F? We don't start knowing that its p norm is small for some p bigger than 1. We just take an arbitrary F. Okay, so let me tell you this convolution conjecture of Talagrand. Okay, so we have a function on a discrete cube. F is non-negative, and this is sort of just normalization. Let's say that the expectation of F is 1. Okay, so the best thing to think about throughout the talk, I mean, the case which is going to be the most difficult is when F is just the indicator, the scaled indicator of a subset. Okay, so you can just think about F as being basically a uniform on some subset. Okay, so what can you say in this case? I mean, obviously, with this much information, not much. You have Markov's inequality. So here this is, again, this probability with respect to the uniform measure. So, okay, probability F is bigger than alpha is at most 1 over alpha. That's Markov's inequality. That's not very surprising. Of course, this is tight if we take F to be the indicator of a subset. Here's Talagrand's conjecture, which is, I guess, it's not inflation adjusted, unfortunately. I mean, it should be right. It shouldn't be the case that things become less valuable over time. I mean, the longer it takes to solve, it should be worth more money, right? All right, sorry.
Maybe not with the parallel adjusted.
It's true.
Really, conjectures, I mean, the work should be stated with the inflation factor.
You should start this transition by offering some money on that with interest, and then people will follow.
Yeah, okay, so the conjecture is that if we apply some noise to the function, then Markov's inequality is not tight. You can do better than Markov if we apply some noise. So at least qualitatively, if you take some noise function, then it cannot look like a step function. So quantitatively, what does it say? Okay, so just fix epsilon. Epsilon is the amount of noise we're going to apply. Then the claim is that there exists some phi such that the probability that the noise function is bigger than alpha is at most 1 over alpha times some phi of alpha, where phi alpha goes to 0 as alpha goes to infinity. Okay? So there's sort of this is not a step function in the strong sense that the tails have some sort of they beat Markov's inequality uniformly. Okay.
So just to capture the fact that the Markov is directed for each alpha, it's directed to another alpha.
Yeah, for each yes, for each. I mean, if you fixed f, then of course this is trivial. You can't keep having mass above. Yeah. So, yeah. But let me. This is the original form, and the next slide I'll have a version which I like better. It's a bit more intuitive. Okay. So a few notes. The first thing is that the best function you can probably achieve here is 1 over square root log alpha, and that's tight if you take f to be the indicator of a suitably chosen half space in the discrete cube. So if you take f to be a threshold function. And the conjecture in the $1,000 is still completely open for any value of epsilon, and even if you just consider indicators of sets. Okay, so this is still, no one knows if this has a positive resolution or not. Okay, let me say the version in terms of sort of temperature. This is why anti-concentration of temperature comes in. This is equivalent. This is just a restatement to saying that if you look at so now you look at the noise function, and you look at the sort of the mass that the noise function can put on a single level set between alpha and 2 alpha. Okay. Then the claim is that it cannot put an arbitrarily large amount of mass on an arbitrarily high level set. So if you make the level larger and larger, the amount of mass it can put there has to go to 0. So this is the sort of So if you look at this picture from the first slide, and if you allow the heat to evolve for a bit, then you get this picture. And so you can see that it's what you expect, which is that when you apply you let heat diffuse. So from this high value you should go to 0 gradually, which means that you hit many temperatures along the way, which means that you can't have all the temperature sitting at a single level. Okay. So this is all still the conjecture. The conjecture is still open. Yeah. Even for in this case, the way it's defined. Epsilon equals 1 is trivial because the function becomes constant, but it's not known for any non-trivial epsilon. Yeah. Even if you flip the coordinates, even if you re-randomize the coordinates 99% of the time, it's still open. Yes.
So what you're saying is the conjecture is that if you soup of the expectation and then let that go to infinity, then this thing should go to 0.
Here the quantifiers are that there exists a phi of alpha, such that for every epsilon there exists a phi sub epsilon, such that this holds for every f and alpha. But the point is, phi alpha here is uniform, so you don't you don't get to take you take a supremum over f's inside.
Over f on the left and on the left, right?
Yeah. Yes. So sorry. That's yes. You have a sup over f on the left hand side. Good. Right. Yeah, so the point is that it's a uniform estimate. I mean, if you give me any finite mass function, then of course, if I go high enough, I will stop finding mass.
Is it different to just say that the expected value in the set between 2 to the I and 2 to the I plus 1 was
Yes, but uniformly, but independent of the function. Yeah. Yeah, that's the same. Okay, so as usual, an interesting case to consider when we can't solve the discrete case is the case for Gaussian space. Okay, so as is often the case, and as will be here, when you want to prove a dimension-free inequality, sort of the analog for Gaussian space is usually a special case of the discrete cube. So it's also the case here, and people studied this version as well. Okay, so here's the Gaussian version. Now we take a function Rn. Now whenever I write expectation, we're done with the discrete cube. So whenever I write expectation, it's respect to the standard Gaussian density on Rn. Okay, and now I want to tell you what is the Gaussian analog of this conjecture. Okay, so let Bt be an n-dimensional Brownian motion, started from 0. If you don't, okay, that's a picture. This is like the least illuminating picture in the world. Okay, So, all right, so the picture was unhelpful. And then we'll define this semigroup. Okay, so it maps a function f to a new function pt of f, which is the result of doing the following. To evaluate pt f at x, you come to x, and then you average the value of f around the Brownian motion run for time t starting at x. Okay, so the point is that, I mean, the Brownian motion will be important for us soon, but this is just saying that you go to x and then you take a Gaussian with variance t, and you average with respect to this Gaussian. So this is sort of we average f in a small ball around x. Okay. No, it's actually no because no. So this okay. So I guess I was. No. The problem here is that the Gaussian measure is not stationary with respect to pt. So if you start on the cube at a point and you do random walk, eventually you go to the uniform measure. If you start at 0 and you do Brownian motion, you don't go to the Gaussian measure. You go somewhere far away. So the problem is right. So we'll see in a second what the correct analog is, but the correct analog should be this Ornstein-Uhlenbeck thing, which it represents the fact that sort of the density of, if you think about heat flow, the density of Gaussian space is non-uniform. So there's sort of like, if you just think about the density of material, then the way that heat will diffuse is not like it would in a flat Rn. But okay. Right. No. So this is the correct semigroup in Rn, but then you will not be able to. Yeah, it's not compact, so you will not have a. But in Gaussian space, you can. Okay, there is a corresponding. We'll see it in a second. Yeah. Okay. So this is the Gaussian of variance t here. Okay. This was just that if you take t equals 0, then you're not doing anything to f. You're just averaging it over nothing, so it's just f of x. And if you take p1, will sort of like, for us, that will be the other extreme point. Then you're just you're just looking at the average value around a standard n-dimensional Gaussian. But that's why this is actually bad, because we would want it to be the case that when you take p1, actually you're just looking at the expected value of f with respect. We would like it to be that p1 is this. But it's not, given if you start from a different x, then you're averaging out here. So this is not quite the right semigroup, but okay. So now we have this averaging with respect to Brownian motion. So here's the Gaussian version of the conjecture, and this will sort of bring up. I mean, here we'll see the sort of the phenomenon that was discussing with Avi. So the conjecture is it's exactly the same thing. That when you apply some noise to the function, you should get tails that are better than Markov's inequality. It's just that this is what we're evaluating now. Okay, so B sub t is a Brownian motion. This kind of at time t. It starts. No. Okay, so the right way to think about this is that the natural way to sample from the Gaussian is just take a Brownian motion to time 1. Instead, what we'll do to sample this is we'll take a Brownian motion to time t and then just average over the rest of the future to time 1.
Why is that then? Because you start at 0, you get the.
So the night. I mean, if you sort of if you do this like random. If you sample according to this thing, then what will happen when you first will run Brownian motion to time t, and then you'll sample, then you'll average over another Brownian motion run for time 1 minus t. So what you'll be doing when you sort of like the arguments you're applying f to are exactly a Brownian motion at time 1, which is which is the Gaussian measure. So this
1 minus t is negative.
1 minus t is positive. No. Think about t as less than 1. So okay, do I have some? Okay. Yeah, you should think about it like this. The natural way to sample, if you f of x, or x according to the Gaussian measure, is just run a Brownian motion to time 1. Okay? But now I want to do something smoother. So I'll run the Brownian motion to time t, and then, normally I would keep running to time 1, but instead I'll just average over the last 1 minus t part of the space. Right? So sort of, this is the quantity I'm looking at. I run to time t, and then I just average over the rest. The point is that sort of that, like, if you average all of these densities, you're getting the standard Gaussian density. Right? So because this is bt plus b1 minus t, which is b1, which is the. Okay. So I mean, if t is equal to 1, if t is equal to is this the right? If t is, yeah, so if t is equal to, yeah, but then I did something, I should say, this should say for every t bigger than 0. Doesn't make sense for every t less than 1, right? No, for t, sorry, yeah, okay, good. For t less than 1, yeah. So, okay, if we set t equals 0, then this function is just the average value of f over the Gaussian measure at t equals 0, because we're just, this is p1, we're just averaging over it. And if we set t equals 1, then there's no averaging, and we're just looking at the value of f at a random point. And in between, there's a mix between averaging and not. Okay? And this really is okay. So this conjecture is a special case of the discrete cube. This is the correct process. Right? And again, it's because this sort of, okay, I'm not writing, I purposely didn't write the Ornstein-Uhlenbeck process to sort of, to avoid some, because we don't need it, we'll just need this formulation. But here the point is that sort of the underlying process here is stationary. We're always looking at the Gaussian, the standard n-dimensional measure at the end of the day, which is good. That's the measure we care about. Because you can take you can embed Gaussian space into the discrete cube just using the central limit theorem. So you take you want to take a Gaussian, and then you sort of write it approximated by a sum of random plus minus ones. That'll give you something in the discrete cube, and you can check that okay, everything works out. Okay, it was unknown, just like the discrete cube case. It was previously unknown for any non-trivial t. The only even n equals 1 is not so easy, but n equals 1 is actually an exercise in Ryan O'Donnell's book, so it's really an exercise. I think it's like a start exercise though. And the only previous result was of Ball-Bart, Bednorz, Olishevitz, and Wolf in 2010, which is that this holds in any fixed dimension. Okay, so it holds in dimension 20. That's this is a dimension-free inequality. So as you probably, if you ever looked at such things, the fixed dimension case is not really indicative of what's going on. Yeah. So here you'll have some constant to the n outside. Okay. N is a dimension. Yeah. Yeah. So in some sense, you can take the solution to the one-dimensional case, and then, using some volume argument, you can extend it to fixed dimension. But this is supposed to be dimension-free, so that's okay. Not so conclusive about the status of it. Let me mention also there's a dual version of this, which is isoperimetric, which actually, if you want to think about other spaces besides Gaussian space in the discrete cube, this is I think this is a nicer version to look at. Okay, so here's the dual version. You take a subset of Rn. Here's a subset of Rn, and some fixed t greater than 0. And then here's your task. Okay, you want to find a g which is supported, some function g which is supported on the set S. Okay. Okay. Yeah, I see. This is all right. Okay, sorry. Just for concreteness, let's just write down all right, maybe, never mind. Dear Microsoft. Okay, well, this is, okay, let's just write down what this operator is, just in case. So this is, so Z here is distributed according to the standard Gaussian density. So when you want to apply this noise to G, you put in sum of x and sum of a normal random variable. Okay, and basically this is some Gaussian noise, but with a drift back towards the origin. So that if you sort of like this gives you a stationary process. If you look at what happens when you run the analogous process, if you start from the Gaussian measure, you'll stay in the Gaussian measure. But it's not so important. I should have stated this in the discrete cube where the notation is easier. But you want a function supported on S such that the noised function is at most 1 everywhere. Okay? And your goal is, subject to those constraints, to try to make the expected value of the function as large as possible. Okay? So there's the easy thing to do, right? Okay, just take G to be the function which is 1 on S and 0 outside of S. Then you'll satisfy this bound because G is always at most 1. So of course, I mean, the averaged version of g is also always at most 1. Okay? And what you'll achieve for the average value of f is just the Gaussian measure of s. So the sort of trivial solution to this problem is just take g to be uniform on this set. Okay? This is true for, so far t didn't help here at all. Yeah. Yeah, so this is not a good, you know, if this was a homework problem, I mean, for a specific set S, this was not a good solution. This was the easy solution. Talagrand's conjecture for Gaussian space restated is that actually there is a strategy that does much better. So why should you expect that you can do better than choosing g to be the indicator of S? Well, what you might do is sort of on the interior of S, choose g to be 1. But then as you get to the boundary, get larger and larger, right? And you're, you know, sort of, you're kind of exploiting the fact that if you go to the boundary and maybe you can make g really large and still satisfy this condition, because when you look out, you know, you're smoothing over this piece of space, almost everything you see is off of the set S. So, you know, the average value here is going to get decreased a lot when you average outside of the space. If S is a ball, then it's easy. You would just take, well, a ball, the complement of a ball is a better thing to look at here. Because you want the, you know, this is, you only want to be able to do better, okay, as the measure of the set goes to 0. Which makes sense. As the measure of the set goes to 0, the boundary should become a more substantial part of the set. And therefore, you can do this cheating where you make the function large on the boundary more and more. If you take f, if you take it to be the complement of a ball, then, yeah, then g, you just make it actually, you just support g on the boundary. And you make it as large as you can there. I mean, the way Gaussian space is set up, the boundary, almost all the mass is occurring at the boundary anyway. So, I mean, that's why it's isoperimetric, because you'd like, you know, if you could somehow identify the boundary of the set, then you'd like g to be concentrated there. Okay? And the conjecture is just that, yeah, you can beat this trivial strategy asymptotically. So yeah, so on the only cases in which it is easy is basically on the real line in 1 dimension. If I give you some set in 1 dimension, the right g to take is just take the point of the set that's closest to the origin. I mean, the point of the boundary of the set that's closest to the origin. Okay? And just put g to be basically a delta function there. Right? So g, I mean, g is really supposed to, you know, it seems like g should point at the boundary of the set, but somehow the Gaussian boundary of the set, sort of like the boundary of the set that's close to the origin so that it has a large measure. And the problem of sort of figuring out what that means is, I mean, that's one reason why the conjecture was difficult. Okay, so that's the. All right, so here, okay, so here's the theorem. Joint work with Ronen Eldan. Okay, so we'll resolve the Gaussian case of the conjecture. But actually, well, let me state a more general theorem, and then the conjecture will be a corollary of this theorem. So we take a function with expectation 1 over the Gaussian measure, and let's assume that I'll explain this condition in just a second, that the eigenvalues of the Hessian of log f are all at least minus beta. I'll tell you the geometry behind this condition in a second. It's very intuitive, okay? But let's just state the theorem. Then, you'll notice there's no noise in this theorem. So the theorem is just for arbitrary functions on Gaussian space, subject to some kind of Hessian condition, then you beat Markov's inequality, okay? So probability f is bigger than alpha is at most 1 over alpha times, okay, up to these annoying factors, square root log, 1 over square root log alpha. So this is even the, I mean, this bound up to these factors in the numerator is quantitatively optimal. And okay, and the way to, I'll put the theorem back in a second. The way to think about this Hessian condition is, you know, if you're sitting at a point of f and you want to, you know, you want to increase the value of the function, well, you should head in the direction of the gradient. But here we're going to be interested in actually increasing the value of the function multiplicatively. So in that case, we should head in the direction of the gradient of log of the function. Okay, so if we're sitting here and we head in the direction of the gradient in the direction of the gradient of the logarithm, the logarithm is not. We don't assume it's convex. So it could be that, you know, we start heading up the hill and then very soon we're heading back down the hill. And the eigenvalue condition just says that actually you get to head up the hill a little while before you hit the other side and start heading back down. So this condition will be used to say that if we're at some point, we can always move in the direction of the gradient of log. So we can always move in the direction in which f is increasing multiplicatively for a little while before we start actually heading back down the other side of this slope. So if you think of, I mean, it says somehow that in every, you know, this is in the positive definite sense, right? This is the matrix of partial derivatives. So it just says that in every direction, this function f cannot be too thin, where you just go like this. It has to be a little bit thick in every direction. Okay. So okay, claim is that a correlator of this is the Gaussian conjecture. Okay. So so this follows, and the reason for this is actually just very simple. Here's the reason. If you take any f, then the eigenvalues of the Hessian of log of the smoothed version are always lower bounded below. Okay? This is actually this is the one place where we're actually using the smoothing, just for this one fact. That if you smooth a function, then it gives you this property that if you start heading up, you can't start heading down too fast. Okay? And quantitatively, in terms of the amount of noise that you apply. Okay. So does it make Sanjeev? Does it make
No, it's very fast.
So, and also, and I mean this by the way, this is very easy to prove. You just you prove it for f being a delta function, in which case you're just looking at some Gaussian, and the computation is easy. And then you use the fact that basically a mixture of log convex mixtures is log convex. So you prove it for a delta function, and then use Jensen's inequality. So it's
This is your inequality.
no, this is classical and easy. I don't know if I saw it written down like this before, but certainly the essence of this is contained all over the place, and it's a very easy fact. Okay, so now our goal is going to be to prove this theorem. There's no more. Brownian motion will appear shortly, but in the statement there's no Brownian motion. But before we do that, let me just say, often when you want to prove something like this, you would say, what are the difficult functions f? Like if you're an adversary and you're trying to make the smooth version of f as close to a step function as possible, what should you choose as the difficult one? Okay? So a first natural choice, this is my artist's rendering of a half space, is that you might choose f to be just the indicator on a half space. And why would you do that? Well, half spaces are noise insensitive. So when you apply sort of this heat flow to the half space, the amount that sort of leaks off the half space will be very small because it's a half space. These things are noise insensitive. On the other hand, actually in this case, the half space is also working against you because sort of if you, so what happens here? The adversary chooses this half space, but what the half space does is it sort of pushes, of all sets of a given measure, a half space is the one which pushes the center of mass furthest from the origin. Okay? So if the adversary chooses a half space, then the game is happening as far away from the origin as possible, which is good for us because we're trying to, we're trying to get our gain. Okay, this is the half space. We're trying to get our gain on this slope here, right? Right. We're trying to say, look, okay, actually the smooth version takes many values here. We say, equal amounts of measure, and the further you are from the origin, the better, the larger the density gets as you go towards the origin. So the adversary, it's a little bit subtle. The adversary likes the half space because it's noise insensitive, but not the fact that it makes the game happen far from the origin, which is helping us because we're getting gain in the direction of the origin. Okay.
This is a fact you mentioned before, but actually for the half space you get well
Yeah. Right. So that without these things up here, this is exactly 1 over square root log is what you get for a half space. It actually turns out that another difficult case that was actually the bane of the proof for a while is if you, in a discrete case, for instance, suppose you take f to be the indicator of an error, like an error correcting code, and then you apply some noise to it. So this is like, okay, in Gaussian spaces, this is some kind of dust. Is it possible that you take this f to be sort of an indicator of this dust, and then you apply noise, and by some magic of cancellations, the result is just you get something that looks fairly uniform everywhere and has have some large value? Okay, it's kind of clearly impossible, but this is. But I mean, if you take f to be a code, it also meets this 1 over square root log alpha bound. So somehow it's not so surprising. It's just because around every point of the code, what you see, like from this perspective, is a little half space. But the point is that somehow half spaces although they are probably the unique minimizers, it's kind of there's like good and bad for half spaces. So okay, it's not clear that this has a sort of a unique minimizer, although probably it does. Okay. Okay, so now in the remaining time, let's go into the proof.
The discrete case, the code is good,
Yeah.
it's good including constant.
No, not the constants. I mean, the constants are a little tricky to calculate in these things. But it might be that sort of asymptotically the constant is correct as n as the dimension goes to infinity for a code.
You choose the code according to racing.
Yeah, you choose the if you don't choose the code correctly with like the epsilon, then you'll just get sort of the uniform measure. So yeah, you choose it carefully. I mean, when you sit down and do it by hand, there's no value that works. I mean, it's sort of everything. I mean, right? It's sort of like, you know, these noises around these code words, they're basically disjoint until everything becomes uniform. And there's this play in the middle which is very hard to understand, and I don't actually know what happens. Seems related to sort of the the covering packing problem for codes that always comes up, like what happens when the balls touch before they over. Yeah, it's hard because I'm not sure because really the measure is on an annulus because so it's not, it's a little so here's we have our function f and we know something about we have some Hessian condition on log f. So here's the idea of the proof. We're going to consider this process. Okay, so the process at time 0, this is just a real number, this m sub t. At time 0, it's just the expectation of f, which is 1. And at time m1, it's a real number, which is it's a random number, which is f at a random Gaussian point. And then in between, it sort of interpolates between the two. So ignore this for a second. So what's happening is this mt, we're doing the following. We run Brownian motion for time t, and then we look at the average value of f under this Gaussian variance t. Okay? If you didn't consider, if you just consider sort of the evolution of this thing as t goes from 0 to 1, these are like, this is sort of this is like the semi-group method, and this has a lot of, there's a lot of powerful uses of this. But the idea here is that actually we're going to do more than just consider, noises at various times. We're actually going to consider a coupling of all the noises together. So we're applying, we're choosing, basically this is a random measure. The measure is centered at bt, and its variance is 1 minus t. And we're looking at f under this random measure, and we're going to use the fact that sort of the noised versions are coupled together at various times. Okay? So this is an idea that, Ronen used a lot in his thesis. We're going to use it here with a different twist, which I'll tell you now. Okay, so our goal, if you set things up like this, is to prove that the probability of m1 is bigger than alpha is much less than 1 over alpha. This improved Markov inequality. Okay, so the problem with this is that we're trying to argue about the probability of a small probability event, which is this is a hard thing to do in general because okay. So now just for a second, think about f as, and actually you can do this for the rest of the talk. Think about f as just the uniform. It's just the Gaussian measure on a subset of the space. So f is just basically an indicator. F is an indicator on a set scaled so that it has expectation 1. And the point is that if we just ran Brownian motion, almost all the time at time 1 the Brownian motion ends up outside this set. So sort of we're looking at the wrong sample space if we're trying to figure out what happens on this set because we very rarely hit the set. So what we'll do is just instead of Brownian motion, let's consider this different process WT, which is if the Brownian motion doesn't land in the set, you just kill it. You just sort of delete it. Okay? So this is sort of Brownian motion conditioned. WT is going to be Brownian motion conditioned to have the measure which is the Gaussian density on this set at time 1. Okay? So I mean so if we do that, right, our goal was to prove that, say, the probability that you're between alpha and 2 alpha is much less than 1 over alpha. With the new process, it suffices to prove that just this probability goes to 0. Okay? And that's just because the probability that the new process between alpha and 2 alpha is alpha times up to a factor of 2 times probably the old process was there. And I mean, which makes sense. Sort of the new process is distributed according to is basically distributed proportional to f. So if f was here with probability alpha, I mean, f of the new process will be there alpha times here the value of f is alpha times larger than the mean value. So it will be there. So the W1, the conditioned process, will be there alpha times more than the unconditioned process. Okay? But the point is that at least this conditioning achieved what we want, which is now we just need to prove that some probability goes to 0 with alpha instead of, or probably is instead of having to prove that it goes to 0 very fast with alpha. The problem is that, I mean, the conditioning could have totally destroyed the process. I mean, maybe we have no control on this process now. So here's this awesome thing. This is what I would like you to get out of the talk. There's nothing else. Which is that you can describe this conditioned process in a very, very nice way. Okay. So now forget what we said on the last slide. Just consider any process WT. It starts at the origin. Okay. And then WT is going to evolve according to a stochastic differential equation. But I'll tell you this in words. It's not so hard to understand what's going on here. In the following way, when time goes a little bit, what does WT do? Well, it does whatever the Brownian motion did. But then this VT, this is sort of some control parameter. Actually, you get to pick it. Then if I tell you, everything that the Brownian motion has done after time t, you get to choose how to push this process WT. So sort of this is just a general kind of control problem. The Brownian motion is doing something over which you have no control, but at every point in time, you get to respond to what the Brownian motion did and push the process a little in some direction. Okay. Under reasonable conditions on this VT, this stochastic differential equation has a unique solution, blah, blah, blah. But just think about it intuitively at the moment. Okay. So the Brownian motion moves, and then you move along with the Brownian motion, but you say, for instance, I wanted to end up in that set, so I'll push a little bit in the direction of the set. Okay.
So given any set, there is a unique solution that you get Gaussian.
Let's in a second we'll see. There are many, many solutions. Here I'm just giving, this is sort of just the setup. I'm letting you choose VT. You can choose to be whatever you want. And the unique solution part was just that, it's a differential, okay, you have to even say what it means, right? This is an Ito process. There's a whole, literature on how to understand these. But in a suitable sense that this is well defined, this object. That's what I'm trying to say. So again, you gave me this drift VT. So if we integrate, we see that the process, what is the process WT? It's the Brownian motion plus just the integral of whatever drift you applied up to time t. Okay. Okay. So now that was in general for any VT. But now I want to tell you how to choose a specific VT. Okay. So now, right? Remember, our goal is at time 1 we want to end up according to the Gaussian measure on the set S, or according to f times the Gaussian measure. So think about all the drifts which would get you there. Okay. Intuitively, there are some trivial drifts, which is just I can wait all the way until time 1 and then be like, oh, that and I'm very far from the set. Just jump all the way to the Gaussian measure on the set. This is one possible drift. This one is not very nice, okay? So we're going to take an optimal drift that minimizes this quantity, okay? So we want to take, among all the drifts that get us to be uniform, get us distributed at time 1 according to the Gaussian measure on our set S, we want to take the one that minimizes sort of the total energy that you had to expend to get there, okay? So VT is most formally, VT is a function of the filtration on which the Brownian motion is defined. But you can think about it, it's a function of just the past. And it's a deterministic function of the past. Given what the Brownian motion has done, and say given the time t, you get to choose VT. But it depends also on the time. So maybe this is one way to think about it. It depends on what the Brownian motion did so far and the current time. And then you get to pick VT in a deterministic fashion. And you're trying to, and the goal is to minimize this. So if you really wanted to follow the sadomasochism theme of the abstract, this is somehow, here you would be minimizing this is the amount of pain that this process is feeling. Naturally it wants to be a Brownian motion, but you're pushing it in some direction. Okay. So here's some, so it turns out there's a unique minimizer here, and this is called Fulmer's drift. It comes out of work in sort of stochastic control theory. And it has some great properties. One of the properties is just that it has an explicit form. Okay, so
why isn't zero drift?
no, there was a condition that the drift has to be such that at time 1 you're uniform on the set S according to the Gaussian measure. Right. So if you could just do nothing for a long time, but then you're going to have to jump really far. So you're better off trying. You don't know what the Brownian motion is going to do. There's some uncertainty in the future. But you're better off trying to sort of push generally in the direction of the set the whole time and hope that. By the end, you're close enough that in your last fits of desperation, you can get to the set. Now, okay, one nice thing, it has an explicit form. Okay, so it's the Vt at time t is just the you look exactly at the gradient, sort of the direction in which the function is increasing multiplicatively, but it's sort of like if you think about this is like incomplete information. You don't look at f, you look at the noise version of it. You look at the average value over the future. Okay? So you don't look at the direction in which f is increasing. You look at the direction in which the f is increasing on average over the future. This makes sense. Okay? So here, for Sanjeev, I told you there'd be multiplicative weights. This is basically multiplicative weights update. That's the fact that it's the log is the multiplicative part, and you're just heading in the direction of the gradient. But if you just did follow the leader, which means that you just sort of tried to go in the direction that f is increasing, it wouldn't work so well for you because it's not taking into account what the Brownian motion is going to do. Right? If the Brownian motion happens to go towards your set, you'd like to take advantage of that. Right? So you don't want to make all your decisions now. You want to sort of like hedge between making a decision about where to go now and also allowing the fact that in the future the Brownian motion might actually help you out and itself get closer to your set. Right? Okay. So this is actually so this is really multiplicative weights, and so then it's not this formula is not so surprising, but this is a beautiful result of Joseph Lehec, that actually this minimum energy exactly gives you the relative entropy of f with respect to the Gaussian measure. So, the expectation is over, over everything here. It's over the Brownian. Yeah, okay. There's only the Brownian motion. Yeah. So sort of you can think about is a characterization of the relative entropy in terms of the average amount of energy you need to expend to push a Brownian motion to be distributed according to f. Okay. So definitely you probably want the process. You probably want some process for which such that the underlying measure is stationary with respect to that process. But you can prove a similar thing on the discrete cube, for instance. The problem is that in Gaussian space, because of Ito's formula, which we won't go into, there are no error terms here. Here there's a logarithm, and this square is the usual square that comes out when you do Taylor expansion of the logarithm. The first order term goes away because you're taking expectation. But you don't get the rest of the terms by the magic of by the magic of Ito calculus that we won't go into. This seems to be a very general kind of phenomenon. So for instance, I'll mention at the end, but you can prove, for instance, the Log-Sobolev inequality for the symmetric group using a formulation like this. So here I want to give a geometric view of what Vt is. So here's the geometric view of what this vector looks like. Your process, here's your process Wt at time t. So what you do is you take a Gaussian of variance 1 minus t. You look at the average, let's say f is a set. So you look at the measure, you look at f under this measure, which is a Gaussian centered at your Wt. And then Vt is just going to be the vector that points from Wt to the center of mass of the set under this measure. So it makes sense. Sort of this is your worldview, and so you head in the direction of the center of mass given your worldview. Except one thing that's not quite true. It's this vector divided by 1 minus t. So this represents the fact that if you're close to time 1 and you haven't gotten to the set, but you have to get there, you get more desperate as time gets closer and closer to 1. Okay.
So what's the length of this vector? Actually, the vector starts at the point coming here close to the center.
Yeah, it's exactly this vector divided by 1 minus t. So divided by this factor that goes to infinity as you approach time 1, which guarantees, this is what guarantees that you'll always end up in the set. And then here's something that's going to be very important. This Vt is a martingale. Okay? So what it means, so if you look at the vector Vt, then condition on where it is now, its expected value in the future is exactly this. This makes sense from the fact that it's an energy minimizer. If there was some kind of, if at this point in time I knew that in the future there was going to be some kind of bias away from where I am now, in order to minimize the energy, probably I should have spent that bias already, right? If I really knew exactly, suppose my set's a half space, in which case that this Vt will just point in the direction of the half space the whole time, then to minimize the energy, I want the norm of Vt to be constant the whole time, right? I have to get somewhere, and in time 1, if I want to minimize the energy, I want to go at a constant speed. So okay, so the point is that if this thing, you can prove it's a martingale, but intuitively the reason that it's a martingale is because if there was going to be some bias in the future, I should have already spent that bias because I'm trying to minimize the amount of energy. Okay, so this is the all right. So here's the setup for everything. We have this is our process WT. This is VT. Okay, so this is, I mean, if you think about what this means, it exactly means that it points in the center of mass of this set. And here there's actually, okay, here's a video. It's not the best video in the world, but this is okay. The set, the set here is just the union of these orange blobs is the set S, and then this is the process. The blue arrow is VT, and these black things, this is the representing the Gaussian distribution along which VT is averaging. Okay, and the last, okay, let me do it one more time. But I mean, it's a pretty cool process. You see at the beginning, well, here things are symmetric, so there's a lot of indecision about where to go. But once it figures out where it wants to go, then it very quickly tries to make the VT constant along the path. I got really annoyed with it because I couldn't get it to go to one of the big ones. So in the very last iteration, I doubled the measure of the big one, so it finally gets there. Okay. This is an annoying thing about Gaussian space. I mean, the measure drops off pretty fast. Okay, so that's the process. And the nice thing about this process, I mean, here's one interesting fact, is that it studies the geometry of F from sort of multiple granularities. Okay, so so for instance, the expected norm of VT squared at time t is this square root is it's hard to. Okay, let's ignore the square root for a second. This is like the surface area of the noised set. Okay, so it's sort of, yeah. So I mean, you look at the set from various granularities and sort of you measure its surface area with respect to all of them. This is all reflected in this process VT. Okay, this seems like a very, I mean, this is a beautiful process. Okay, so now to finish the proof sketch in our last 5 minutes. Okay, so we want to prove that the probability here in this interval alpha to 2 alpha goes to 0. Okay, so here's how we're going to do it. Well, we'll show that, suppose that the probability there is p, then we'll try to show that actually the probability between 2 alpha and 4 alpha is p, and also between 4 alpha and 8 alpha is p. And if we do this for enough levels, then it means that, by the fact that probability is sum to 1, that the initial probability must have been at most 1 over the square root of log alpha. Okay? So the goal is just to take this mass and then argue that we can push it to higher level sets. Okay. Okay, so the first thing is so given this condition, we'll try to make F bigger. Okay, so how can we make F bigger? Okay, so we can push in some direction u. Okay, so this is where we are at time 1. So let's push in the direction u. What happens? We get this plus some gradient term. Okay, the inner product between u and the gradient of the logarithm. But also, of course, there's a second order correction, and this is where this beta comes into play. We know that the second order correction is not too big. So this is just exactly says that at time, we can push in the direction u. We get some, if u is going in the direction of the gradient, we get some gain. Okay, except this second order correction. Yeah.
What is going to be VT?
So no. Okay, so now, so ignore VT for a second. We're trying to prove that if f of w1 ends up here, then we can also get it to end up here. So I'm doing the trivial thing, which is just say, okay, well, let's just push it in the direction of the gradient. We'll get it to be larger. This is not a greatest strategy, as we'll see in a second. Yeah, this is basically the reason. If you push too hard, then this u squared starts to kill you. It's exactly the fact that you can't go for too far. You can't push too far in the direction of the gradient. Okay, so this is so remember that v1, this process is exactly the gradient of the log. So this says that if we push in the direction of u, then we get some gain. Yeah. This is all equal. This is p over 100, and if you want square root log alpha, you can't even do this. This gets log alpha to the 1/4 or something. But this is still the basic idea. Okay, so if we know what happens if we push in the direction u, the gradient at time 1 is this v1. Okay, so we get this minus some correction term. Okay, so if we take away the logs, if we exponentiate both sides, so let's suppose we push a little bit in the direction of v1. Remember, v1 is the direction of the gradient. Then, if this delta is small enough, this term, this is a quadratic term. So this is paying delta squared versus delta. So this term is going to beat this term if delta is small enough. And then we'll get some multiplicative increase in the value of f. OK, so that's good for us. But what you should say to yourself is, who cares? I mean, yeah, I can make the function bigger. But I wanted to argue that W1 could have achieved this gain. You're telling me that you can achieve this gain. That's not very impressive. But the idea is sort of the following. If you think about Brownian motion, so if this is Brownian motion, and we push Brownian motion a little bit in some direction, there's a decent probability that actually Brownian motion could have gotten there itself, because Brownian motion has some variance, some natural variance. So, if we push Brownian motion a little bit, then the probability that Brownian motion actually got here, this is all in the sense of, it's probably 0, but should be not too much smaller than it was here. Okay, and so we would hope to use that. We would hope to say that if we push this process a little bit, then there's some probability that W1 could have done this push itself, right? Because W1 is driven by Brownian motion. So there's some probability the underlying Brownian motion could have achieved this push. And say it again. At the same time. So yeah, so in general for the same t, right? If I push Brownian motion a little bit, you can calculate. It's actually not hard. The sort of the change of measure of to go from here to here. Okay. So the point is that So here's Girsanov's theorem, which is a general change of measure formula. Which is exactly, this is a beautiful fact, which exactly is going to say the following. If I have this is supposed to be a d here, so I apologize. This is dxt. But I have some process which is Brownian motion plus some drift. Then there's an exact formula for the probability that Brownian motion itself could have just simulated this drift. Okay? And the change of measure is just this. So so this term makes sense. Both terms actually make sense, but this is sort of the change of measure. So for every path of this process, I claim that the Brownian motion could have achieved that path with some probability, and this is the weight you should put on that path. So it makes sense if if Vt is large, then the probability Brownian motion would have done it is going down exponentially, actually in the energy of Vt. And then this term just represents the fact that this is the main term here. This is going to be a lower order term, but if you push in the direction, actually if you push in the direction opposite of the Brownian motion, then if the Brownian motion goes in some direction and you push even more in that direction, you'll have to pay more naturally. But this is the main term here. This is sort of the cost you pay. So the point is that if we do this push, it's possible that we can say that the original process would have made this push by itself, except for the fact that that only holds if we push sort of slowly. Here in the previous slide we were pushing at the end. This is not good. So actually, instead of pushing at the end, we want to push the process slowly the whole time. Okay, so that's the masochistic part of the proof. So we know so this is the new process we're going to use. So this is the old process, and instead of just pushing it in the direction of the gradient at time 1, let's just at every point push it a little bit more in the direction of the gradient at that point in time. So given some delta, this is a new stochastic process, which is just a little more greedy than the original process. It goes a little more in the direction of the gradient. Okay, and the point is that since we're only adjusting this process sort of along the filtration, along the Brownian motion, now Girsanov will allow us to say that there's a reasonable chance that Wt would have done whatever xt does. Okay, so this push we can cope with, and we can say that if this new process had done something, Wt could have also done it. The problem now is that we lost the condition we had initially, which is that it's not clear that being greedy actually increases the value of f at the end. It's intuitively clear that it should be the case that if you had more in the direction of the gradient, then the value of f at the end should be larger. But it's not clear. Okay, so now just note that this is x. This is x1. So x1 is our original process w1 plus this additional push. Okay, and recall this formula that we had that if we push in direction u, then we get a gain if u is correlated with v1. And so the question now that sort of is the main technical point of the proof is if we push on average the whole time, is that somehow correlated with the direction we're pointing at the end? Right? So now there's this process that's going like this the whole time. We're pushing more in the direction of the gradient. And the question is sort of the average value of the push correlated with the gradient at the end of the process? Okay. So sort of if you remember this picture, it seems like it was in this animation, right? Once the process figured out where it wanted to go, it sort of pointed kind of in the same direction the whole time. Okay? And the saving grace here is going to be the fact that this VT is a martingale. And therefore, the expected value at any time at V1, conditioned on where it is at VT, is exactly VT.
Is the weight
The 1 over 1 minus t only affects this. There's some little of one term that I wrote. Where was it? It's here. It's only this error term is affected by the t. So let's ignore this for now. But it does affect how much we can push the process. Okay. But at the end of the game, the game that gets played. I'm going to go into the last slide in just a second. The game that gets played is that you want that the increase in the value of the function due to this push is exactly compensated for by the decrease in the probability that the Brownian motion would have done that. Okay? So sort of like in the change of measure, you get some term that looks like this. And in the increase in the function, you get a term that looks like this. And now from the fact that VT is a martingale, at least in expectation, the increase you get from the push exactly cancels out the decrease. The fact that the path you're using has smaller measure, because the Brownian motion would have done it less likely. Okay, and now just the point is that the difficult part of the proof is that this is all an expectation, and now you need these things to actually hold at the same time and be concentrated. So the difficult part of the proof here is concentration, but the main point is that the loss in probability is exactly made up for by the gain in the value of the function, which is exactly what you want if you go back to the original setting, right? You want to say that the amount of mass at some temperature can't be too concentrated. So when you push up one level, of course, the value of the function, say, doubles, but the probability should halve. So this is exactly the kind of picture one wants. Okay, so you can, if you do this correctly, you get something with 1 over square log alpha. Okay, so you can do this in general spaces, like you can do it in a discrete cube, for instance, the same kind of drift process. It gives very easy proofs of it gives like a one-line proof of the Log-Sobolev inequality for the discrete cube. It gives a proof of Log-Sobolev in the symmetric group, and you can say more general things. Okay, although all these proofs only use sort of first derivatives, whereas one of the new advents of our proof is that we use the second order condition on f. We use something about the Hessians. Okay, so maybe this is very useful. The reason we can't extend it to the discrete cube is it's just because the push in the Gaussian case was deterministic. If I told you what the Brownian motion was, then you just told me the direction you wanted to go. If you want to do the same process in the discrete cube, then it's some kind of correlated sampling. You have some process which is flipping fair random coins, and you're trying to bias the random coins to push to push to a different measure. But how do you bias a coin? You just need some additional randomness. Like if the coin comes up heads, then sometimes I'll flip it back to tails. So sort of the fact that you have a continuous filtration in the Gaussian space means that the drift can be like deterministic, whereas in the discrete case you need some additional randomness, and this actually messes up the concentration in a seemingly serious way. I mean, not like an insurmountable way, but a way that makes it difficult. All the stuff with Girsanov works because you can just think about this actually as information theoretically. It's some kind of mutual information between two processes. The difficult thing is that, the difficult thing is that here you push in some direction. I mean, basically what happens in a discrete cube is, you push in some direction. You don't end up at a discrete point. You'll end up somewhere in the you can extend f to the continuous cube. You end up somewhere there. Now this point is a mixture of discrete points, but it's perfectly possible that the discrete function just sits at two different levels, and yet inside there's anti-concentration inside the cube because it's an average of these two levels. But when you sort of jump from a continuous point to a discrete point, you don't get this. I mean, you could just get the one of two level sets, and we don't know how to fix this problem. Okay, I think there's a lot of things that one could hope to do. Here's a very nice information theoretic question, which I'll end the talk with, of Kumar and Courtade, which is it's the following: X is a uniformly random n-bit string, and let's say Y is an epsilon noise version of X. Okay, and now what you want to do is you want to among all functions that map n bits to 1 bit, you want to maximize the mutual information between, like you get to output 1 bit about X, and you want to maximize the mutual information between this 1 bit and the string Y. Okay? So I have 2 correlated strings. I get to output 1 bit about one of them, and I want that bit to have as much information about the other string as possible. Okay? Yeah. So this is the natural thing to do, which is just to output the first bit. Okay? The conjecture is that this is the best thing to do, but it's despite being tantalizingly simple, it's still open. Is it still open? Okay, you smiled, so I thought maybe you solved it in the.
I think it has $500.
Oh, that's not.
Inflation adjusted?
Okay, so I'll end with this open question. Thanks.
Just to be sure in the picture, so where you have the video, the points are not supposed to die at the boundary of the inside, right?
They should go inside. Although, I mean, well, for the little ones you can't really see. For the big ones, you know, you almost thought, you know, the Gaussian measure was much larger near the boundary. But you should take these animations with a grain of salt too, because you know, this was like me coding it up in like a couple hours, and there could be some numerical instability issues. I had to cheat a little bit. At the origin, at the very beginning, when it doesn't know which way to go, like the first step, you know, is very important. So if you don't have enough precision. Yeah.
So I'm thinking about the discrete view where one continuous thing close to it that doesn't look like Gaussian space, but we should look at the solid cube and the noise operator at any point in a particular direction when we just keep it all uniform on the line.
Yeah. For the solid cube,
In the solid cube, so
Yeah.
can
this works for the solid cube.
work
Yeah.
for this kind
Yeah.
of noise operator?
Yes.
You cannot.
Well, yeah. I mean,
You may be able to discretize it not to the discrete view, but to the discrete grid with more.
that will also work. But yeah, the problem, I mean, the natural thing to do if you want to work with the discrete cube is take the function on the discrete cube, and then just take the harmonic extension to the inside. This is a natural extension. And then you can prove that anti-concentration for the harmonic extension. But that doesn't imply that F is not concentrated. I mean, that you can prove that really doesn't imply. There are examples, right? I mean, you can. So there's one thing we don't understand yet for discrete spaces.